Now we're ready to apply this idea of a difference of two population means. The idea is we're going to use two sample means from two different populations to really make an inference about a difference of population means that we don't actually observe. So let's look at this study. This is a study about fat mice. The idea behind this, and this is a real data set, it's a real study that made a lot of news. It's from a well-regarded academic journal, and what they wanted to know is does exposure to light at night, does it affect weight gain? Now they used mice, but they were really trying to generalize to humans. They wanted to say, well, if it's true for mice, then it's probably true for humans. So they're trying to generalize to humans, but for the purposes of really the data at hand, it's a collection of mice. And they randomly assign different groups of mice to different treatment and control groups. So what they wanted to know specifically was they wanted to examine body mass gain in mice after 4 weeks for mice, for those who are exposed to a normal cycle of light and dark as compared to a set of mice who are exposed to bright light at night. Okay, so we're going to label these two groups LD and LL. The normal group, light and dark cycle, that's what you'd expect to experience if you didn't have access to any kind of electronics at night. You would just be exposed to light during the day and dark at night. While the bright light at night, the idea is that this kind of mimics what we are all exposed to in today's world when we use electronic devices at night. The idea is that what happens if you just give mice light all the time? Right? And what they found after 4 weeks, after randomly assigning mice to either the first group or the second group, what they found is that those who were exposed to light during the day and no light at night or dark at night, they gained about 5.89 grams. And then in comparison, those who were exposed to light during the day and light at night, they gained almost twice as much in terms of 10.89 grams. So the sample sizes for these two groups, they're 9 mice, and the standard deviations are roughly comparable. So the null alternative hypotheses here, well, they're expressed in this way. The null is that the mice groups have the same weight gain, so their difference is 0. The idea is, well, in the population, the mean of one group and the mean of the other group, they're 0. And the population here you have to think of is sort of the set of all mice. Okay? They use a sample of mice and they're trying to generalize to all mice. And then the alternative is simply that the difference is not 0. Right? They think that light at night will in fact increase weight gain, but they're open to different conclusions. Maybe it's possible. They're open to the idea that maybe light at night would actually decrease weight. So the idea here is that we will use that group of mice exposed to light during the day and light at night, that's group 1, and the other group of mice exposed to light during the day and dark at night, that's group 2. And so we're going to express these hypotheses as the null is that mu1 minus mu2 equals 0 versus the alternative that mu1 minus mu2 does not equal to 0. And we're going to use the independent samples t-test to compare the difference in means. This is the actual data set of mice. So you can see the cases, the observational units, the rows are these different mice. So we have 18 mice, and then we have 2 variables for this particular data set. We have the treatment and control conditions, so that's the variable light. Either mice were exposed to LL or LD. LD is the control group, LL is the treatment group, meaning LD is that group of mice that were exposed to a regular cycle of light during the day, dark at night, and then the treatment group of mice was exposed to light during the day and light at night. And then we have this variable of weight gain. So after 1 month, after 4 weeks, they tracked these mice and they saw how many grams did they gain. Right? And they were both given access to the same amount of food. So the idea is they're attributing this weight gain or weight loss in some cases, possibly, to this treatment and control condition. So let's look at this result using a 2-sample independent t-test. Recall that we're going to use statistical software when we conduct this t-test. It's because these test statistics are really a pain to calculate by hand. So when we use statistical software, we get this kind of output. Right? We can use the critical value from this output to make a conclusion. So we obtain a t-test statistic of about 4.94, and that's distributed on a t-distribution with, that has roughly 14 degrees of freedom. Recall the degrees of freedom governs the sort of shape of the t-distribution, and we can locate that test statistic on that t-distribution. Based on this critical value, okay, we can really make a conclusion about this critical value and this test statistic. We can really make a conclusion to either reject or fail to reject the null. So this is the t-distribution when we have roughly 14 degrees of freedom. This is what the t-distribution looks like. It looks pretty close to normal, but the tails will be a little bit fatter. It's not completely obvious here, but if you compare it to a normal distribution, you'll see that. The other point to consider is that we have these two alpha levels, okay? Negative t alpha divided by 2 is negative 2.15, and positive t alpha divided by 2 is positive 2.15. If our test statistic in absolute value is greater than t.15, or equivalently, if our test statistic is either in the lower left tail or the upper right tail, okay, then it's really unlikely that we would have obtained that test statistic under the assumption that the null is true, that the difference in population means is 0. And in that case, we reject the null. So for this example, right, for a two-sided test, right, we have this test statistic in absolute value of 4.94, which is much greater than this critical value of 2.15. To put another way, that test statistic, it's in that upper right tail. Right? If that null is true, if the sampling distribution is centered around that null, it's very unlikely that we would have obtained the test statistic of 4.94. So we reject the null, that the difference in population means is 0, and we reject that null at the alpha equals 0.05 level, because our test statistic of 2.15 is based on that alpha level of 0.05. So we reject the null using the critical values approach and the statistical software output. We can also use a p-value, a probability value approach. This is usually more common in the published literature, but they're equivalent, okay? Often a lot of researchers will report the test statistics and the p-values. We obtain a probability or p-value of about 0.0002, right? It's a low p-value, and that's much lower than the benchmark of 0.05 that we're using by convention. So since that p-value is lower than 0.05, we reject the null hypothesis. Right? The null hypothesis states that the difference of the two population means is 0. We reject that null. And that's equivalent to an equivalent conclusion that we would obtain through the critical values approach. Substantively, in using the critical values approach or the p-value approach, we conclude that light exposure at night, it appears to induce weight gain in mice, with the implication that all of us, when we're exposed to electronics at night, and televisions at night, and iPhones and computers and laptops, that light might induce some weight gain. So be careful about using electronic equipment at night. This is what the p-value looks like on our t-distribution. This is the t-distribution based on 14 degrees of freedom. So if the null is true, that sampling distribution, we would expect to be located way off on the side there. And then the p-value, right, it's way in the extreme tail. What that p-value suggests is that the probability of obtaining a test statistic as more extreme than the one we obtained, it's almost 0. It's very low. So it's very unlikely that we would have obtained that test statistic under the assumption that the null is true, that the difference in population means is 0. So our conclusion, we conclude that those mice who were exposed to more light had an increase in weight gain relative to those mice who had a conventional light-dark exposure. Now, of course, whenever you look at a study, you should be careful. You should question the findings. You should think about substantively what is going on here. In this case, are mice the same as humans? Maybe, maybe not. Maybe not. But the other point you should keep in mind is that sometimes we use studies on animals or mice because the question is would this be an ethical study if conducted on humans? In fact, some people would say, is this an ethical study conducted on mice? Right? So these are all considerations when we think about conducting research. And with that, we conclude this first example of using the independent two samples t-test.